The evolution and impact of AI algorithms in modern computing in an era where artificial intelligence is reshaping industries from healthcare to finance. Understanding AI algorithms becomes essential for developers and data scientists alike. These sophisticated mathematical models form the backbone of intelligent systems that can learn, adapt, and make decisions autonomously. This article delves deep into the world of AI algorithms, exploring their origins, classifications, applications across various domains, challenges they pose, and future directions. Whether you're a seasoned programmer or new to machine learning, this guide will equip you with the knowledge necessary to navigate the rapidly evolving landscape of AI technology. Origins and foundations of AI algorithms. The roots of AI algorithms trace back to the mid-20th century when pioneers such as Alan Turing laid down theoretical foundations for computing machines capable of simulating human thought processes. This period marked the beginning of what we now recognize as modern computer science. Turing's concept of the universal machine provided a blueprint for programmable computers, which eventually evolved into complex AI systems. His work set the stage for subsequent breakthroughs by establishing fundamental principles of computation and logic that remain relevant today. Following Turing's contributions, researchers at institutions like MIT and Stanford began developing early rule-based expert systems designed to mimic human decision-making capabilities within specialized fields such as medicine and engineering. These initial efforts were limited by computational power but paved the way for later advancements in neural networks and statistical methods used extensively in contemporary AI research. Categorizing AI algorithms. Supervised versus unsupervised learning. Artificial intelligence algorithms are broadly categorized based on how they acquire knowledge from datasets. Two primary categories include supervised learning and unsupervised learning approaches, each serving distinct purposes depending on available resources and desired outcomes. Supervised learning involves training models using labeled datasets where input-output pairs are clearly defined. Common techniques under this category include regression analysis for predicting continuous values and classification algorithms for categorizing items into predefined classes. Unsupervised learning, conversely, deals with unlabeled data without explicit guidance regarding expected outputs. Clustering algorithms group similar instances together while dimensionality reduction techniques simplify high-dimensional information for easier interpretation. Choosing between these two types depends largely on availability of annotated data. However, semi-supervised methods have emerged as viable alternatives offering benefits from both paradigms simultaneously. Differentiating between deep learning and traditional machine learning. While traditional machine learning relies heavily on feature extraction performed manually before model training begins, deep learning automates this process through layered architectures known as artificial neural networks. Deep learning excels particularly well in handling unstructured data formats including images, audio files, natural language texts due to its ability to detect hierarchical patterns inherent within them naturally. Traditional ML models often struggle with scalability issues related to increasing complexity, whereas deep learning frameworks scale efficiently thanks to distributed computing support offered by cloud platforms nowadays. A significant advantage lies also in reduced dependency upon domain experts who would otherwise need provide carefully curated features suitable for specific tasks being tackled via conventional means alone. Applications across industries. Real-world examples of AI algorithm usage from personalized recommendations on streaming services to autonomous vehicles navigating busy city streets safely. AI algorithms touch nearly every aspect of daily life today. Their versatility makes them indispensable tools across diverse sectors ranging from entertainment to transportation. E-commerce. Retail giants utilize recommendation engines powered by collaborative filtering algorithms to suggest products tailored specifically towards individual preferences, thereby enhancing user experience significantly. Healthcare. In medical diagnostics field, advanced imaging recognition software employs convolutional neural networks, CNNs, effectively identifying tumors or other abnormalities from radiographic scans with remarkable accuracy, surpassing even experienced professionals sometimes. Finance. Banks leverage anomaly detection mechanisms built around random forest classifiers, helping identify fraudulent transactions, quickly reducing potential losses considerably compared to traditional manual reviews. Transportation. Self-driving car manufacturers implement reinforcement learning strategies, allowing vehicles adjust driving behaviors dynamically according to real-time traffic conditions, ensuring safer travel experiences overall. Challenges faced by developers implementing AI algorithms. Despite tremendous progress made thus far, there still exist several hurdles preventing widespread adoption, especially among smaller organizations lacking sufficient technical expertise. Required managing complex AI workflows seamlessly. Data scarcity remains one critical issue impacting performance reliability, since most successful implementations rely heavily upon extensive quality-assured historical records spanning long durations, typically not easily accessible everywhere equally. Computational costs associated running intensive simulations repeatedly consume substantial energy, leading environmental concerns arising concerning carbon footprints generated during processing stages involved. Moreover, ethical considerations surrounding privacy violations, risks posed by misuse sensitive personal identifiable information collected unknowingly by third parties operating behind opaque corporate structures, further complicating matters substantially. Future directions for AI algorithm research and development. Ongoing investigations continue pushing boundaries forward, aiming to address current limitations while unlocking novel possibilities previously deemed impossible technologically speaking until recently. Advancements toward explainable AI seek resolve black box nature, making transparent, understandable predictions interpretable by non-experts, facilitating better trust-building relationships. Crucial business environments requiring accountability. Transparency standards compliance requirements met regularly. Quantum computing integration promises exponential speedups, solving optimization problems encountered frequently within logistics scheduling scenarios where classical counterparts fail, delivering feasible solutions timely manner needed. Commercially practical situations. Federated learning emerges promising approach enabling decentralized collaboration, sharing insights collectively without compromising confidentiality, preserving integrity. Private data sources located remotely, geographically dispersed locations globally. Evaluating performance metrics used to measure success of implemented models to assess effectiveness. Accurately standardized evaluation criteria play vital role determining whether chosen methodology indeed achieves intended objectives. Reliably, consistently over time frames considered acceptable, industry benchmarks established accordingly. Commonly employed metrics vary depending problem type addressed. Precision recall curves, preferred binary classification settings versus ROC/AUC scores utilized, multi-class distinction contexts. Similarly, confusion matrices aid visualizations, misclassification rates occurring frequently confusingly. Similar categories confused, mistakenly classified incorrectly. For regression-based tasks, mean absolute error (MAE) alongside root mean squared error (RMSE) serve popular measures quantifying discrepancies existing predicted actual numeric targets measured against. Ground truth references regarded gold standard comparisons conducted routinely. Cross-validation procedures ensure robustness, eliminating bias, introduced randomly selected samples, drawn disproportionately skewed distributions favoring particular subsets, potentially misleading conclusions derived erroneously, assuming generalizability beyond original dataset scope, unnecessarily extending applicability outside intended usage cases, strictly confined. Pitfalls to avoid when designing or deploying AI systems. Mistakes commonly occur during implementation phase, primarily stemming lack thorough testing, rigorous verification prior deployment commencement, neglecting edge case scenarios possibly overlooked. Initially assumed negligible impact later proved detrimental upon encountering rare occurrences, unexpectedly disrupting operations critically. Overfitting represents serious threat affecting predictive capabilities, severely diminishing utility once applied. External unknown test samples exhibiting different characteristics, diverging markedly, contrasting those seen exclusively during training phases, restricting broader application usefulness, constrained narrowly specific instances only. Bias embedded unintentionally within datasets creates unfair advantages, disadvantaging certain demographics, perpetuating systemic inequities, exacerbating existing disparities, worsening social divisions, creating mistrust, undermining Credibility, perceived legitimacy, initiatives undertaken, purportedly beneficial, public good, intentions genuinely meant, promoting equality, fairness, equitably distributing opportunities fairly, irrespective background circumstances individuals hail from. To mitigate these issues, practitioners must adopt inclusive design philosophies prioritizing diversity representation, ensuring equitable treatment afforded everyone regardless identity attributes held irrespective differences distinguishing people uniquely apart others. Conclusion: the journey through the realm of AI algorithms reveals a dynamic landscape filled with innovation and challenge. As these technologies evolve, so too does our understanding of their implications and potential. By staying informed and engaged with ongoing developments in AI research, programmers and data scientists can harness the power of these algorithms responsibly and effectively. Embracing best practices ensures sustainable growth benefiting society at large, positively shaping future technological landscapes ahead.